So what we'll be looking at today is why we study solutions, and then interconverting between mass solute, mole solute, and molarity. So why study solutions? So why do we worry so much about reactions and solutions? There's several chapters in the book on this. And first, water is everywhere. We see water everywhere we go. In biology, we're mostly water, so almost all the reactions occurring in our body are in aqueous solution. In the environment, everything that's happening in the water that we drink, the water around us, in the oceans is reactions in an aqueous solution. So we really care about that. In chemical engineering, also, if you're trying to produce something, doing a reaction solution is really good. Let me give you an example. Reactions with solid and air are very slow. If you have some solid that you're trying to react, it's only going to react on the surface. And so if you want it to make the reaction happen fast, you want to make a lot of it, it's really hard. The reaction is only occurring at the surface. Even if you have a powder, you grind it up to a powder, you still have a lot more surface area, but you only have the surface of the particles that are reacting. So that's not so great. Even worse is a solid-solid reaction. That's just ridiculously slow. If you have two pieces of metal together and somehow you're trying to get a reaction between them, it's going to be a long time before you get a reaction happening. So in solutions, however, all the reactants are spread throughout the solution. They can find their reaction partners very easily because they're all, even if it's somewhat dilute, you're probably still only, tens of nanometers away from your next reaction partner. So it's much easier to make reactions happen in solution. And therefore you get your product much faster. So both in terms of being able to do something with reactions and understanding what's happening in the world around us, it's very important to understand solutions. Most solutions are aqueous that we deal with in the lab, but certainly not all of them. You can have a solution, any solvent that you're interested in. Most interesting ones are generally aqueous, but there's all sorts of interesting other types of solutions. Okay, so some solutions terminology. A solution, a homogeneous mixture of substances. So we say it's dissolved if the solute, so the solvent, the major component, usually a liquid, but you can have gas solutions as well, where you have something that's dissolved in a gas. A solute, the minor component, could be gas, could be liquid or solid, but then is mixed in and dissolves in that solute. And it dissolves homogeneously with the solvent. If it's not really a solution, it's some sort of suspension. So by this mixes homogeneously means is that at a molecular level, the molecules are separated and the solute molecules have solvent molecules between them. So if it's 99% on a molar basis solution and 1% solute on a molar basis, then on average, each solute is surrounded by about 100, each solute molecule is surrounded by about 100 solvent molecules. So that at a molecular level, it's dissolved into the solution. So typical terminology that a solute is dissolved into the solvent. If a solute will dissolve into a given solvent, it is said to be soluble. If the solvent is water, the solution is called aqueous, but there's certainly all sorts of other solvents. Any liquid you can dissolve in, you can make a solution out of that. Concentrated is when there's lots of dissolved solute in solution. Is there a cutoff for what concentrated is? No. It's in the eye of the beholder. Generally, you'll be looking at multiple solutions. You can say this one is more concentrated and this one is more dilute. Relatively little solute dissolved in solution. Is a 0.1 molar solution concentrated or dilute? I don't know. But if it's about as much as you can put in, 12 molar solution of acid, yeah, that's concentrated. If it's 10 to the minus 9, then it's pretty dilute. There's just not much solute in there. But there's no specific level to say concentrated or dilute. It's a qualitative term. Okay, so now quantifying solution concentration. So concentration is defined as the amount of solute dissolved in an amount solution. So we take the total amount of solute and look at the total amount of solution that we have. Now this is important. It's not the amount of solvent, not the amount of solvent you dissolve it in, but the amount of solution. Remember that. It's the total amount of solution. So if you take a solute and add solvent to it, there's no guarantee that the total volume is going to be the same afterwards. There's the volume that the solute contributes. There could be interactions that reduce or increase the volume. So at the end, you want to look at the amount of solute you put in solution. Why is this? Well, really, so solution concentration is a way to relate something we can measure, volume, to an amount of moles. So that's the key. We want to be able to measure the solvent. We don't get to measure the solvent that we put in. We get to measure the solution that we have afterwards. So it's the amount of solute dissolved in the amount solution. Okay, so what the units? The units are moles per liter. So you'd have moles ethanol of solute per liter solution. So they're both amounts, but one's an amount in moles and the other is an amount in volume, in liters. So it's moles per liter or moles per other volume. But the general concentration, the molar concentration is moles per liter. That's the canonical unit. So molarity, as I said before, allows us to convert between volume solution and amount solute. In the same way before that we had mass of reactant that allows us to relate to the number of moles of reactant. Here we can take the volume of solution, something we can measure very easily. So we can measure in a graduated cylinder and relate that to the number of moles of solute that's contained. So the same way as before, relating the thing we need in a reaction, the number of things, to a volume that we can measure because we can't count atoms. Okay, so let's say we have 5 liters of a 0.5 molar solution of ethanol. How much ethanol is it? So we'll switch to the other view. And if we have 0.5 liters solution, and the molarity is 0.5 moles of ethanol. I'm writing it out very precisely here, per 1 liter solution. That gives us the liter solution canceled, and that gives us 0.25 moles of ethanol. So so it allows us to convert volume to things because we can measure volume easily. We can't measure number of things. Okay, so that's the basic definition. So let's start doing some practical things with this. We have, okay, how many grams of lead nitrate are needed to make 250 milliliters of a 0.1 molar aqueous solution? We assume we have enough water to do this. We just need to figure out how many grams of lead nitrate need to go into it. So lead nitrate, what we need to do, if we're going to put lead nitrate in, we need to know not how many grams we're putting in, but how many moles we're putting in. So we need the molar mass. We need the molar mass of lead nitrate, PbNO3, and there's 2 of them because nitrate has a +1 charge. In this case, sorry, -1 charge. Lead has a +2 in this case. And we have 207.2 plus 2 times 14.01 plus there's 6 oxygens because there's 2 nitrates and 3 oxygens per nitrate, 6, 2.00. That gives 331.2 grams. Let's just call it lead nitrate here. That's not lead nitrogen, that's lead nitrate. Mole of lead nitrate. I'm just writing it like that so I can squeeze everything in on the page. And so we have 250 mils. Now it's important that molarity is defined in terms of moles per liter. So we need to convert from milliliters into liters times 0.1 moles per liter. And so these cancel. These are, remember, liters and milliliters of solution. Those cancel. And then we have, that's the moles of lead nitrate. And we have that 331.2 grams of lead nitrate. For 1 mole of lead nitrate, and those cancel, and when we multiply everything together, and given that we have two significant digits, 8.3 grams of lead nitrate. So what we would do, we would weigh out 8.3 grams of lead nitrate, start to being careful because lead can be toxic, and pour in some water, mix it up, keep stirring it, pour it enough that it dissolves. Once it dissolves, then we gradually add water in, keeping it stirring until we reach 250 milliliters. Because then we'll have 250 milliliters solution, not 250 milliliters water plus lead nitrate, which might be a little different than 250 milliliters. So that is how we would figure out how we make a solution of a given molarity.